Thank you all for coming. It's a really pleasure to be here on the Deep Tech stage. I've been told that this is the nerd audience, so I feel like I'm in the right place at least. But really looking forward to talking to you all about these two topics. So before I get started, how many of you have heard of quantum? Okay, so that's everybody. How many of you have heard about this little thing called artificial intelligence? All right. And how many of you actually have a good sense for how the two of them come together to do something that's practical? Okay. Fewer hands up. So that's really what I want to talk about today. So both of these technologies are fascinating in and of themselves. They are both have a huge potential for being disruptive for many different verticals, for many different applications. But I find that it's really the convergence of those two technologies that's super exciting. So that's what I'm going to focus on for my talk. And I'm also going to focus on a little bit of the healthcare application and how this convergence of quantum and AI can actually provide a big impact. So my name is Nadia Carlsten. I lead product at SandboxAQ. SandboxAQ is a company that spun out of Alphabet Google about last year, and our goal is to really bring quantum and AI to solve big problems that are impacting society. We have several different products. Our products are focused on three main areas: quantum sensing, as well as security and quantum simulation. So obviously, both quantum and AI are very big parts of those product lines, and I'll touch on that in a little bit. So if you've been paying attention, and you all have because you raised your hands when I asked about quantum, you know that quantum is a huge topic these days. It's thought to be a huge paradigm shift. I fully believe in that. Prior to Sandbox, I was at Amazon heading product for quantum computing initiatives. So I fully believe in this thing called quantum. But I think where the disconnect with a lot of people is how does it actually do something useful? How does it actually impact any sort of applications? So the way to think about quantum is really doing computation in a way that's more efficient. And that's not all of computation. It's just certain problems that can be done more efficiently on quantum computers. So just to give a quick background so that everybody's on the same baseline, when we talk about quantum computing and we contrast it with classical computing and what you think about as normal computers, the big difference is having bits versus qubits. And so with bits, it's basically zeros and ones. You can think about it as an on and off switch. You can only be in one of those two positions. Whereas with qubits, you can actually be in a state that is a combination of both 0 and 1. A very simplistic way to think about it is to think about flipping a coin. And while you're in that process and the coin is still up in the air, you don't really know if it's going to be a 0 and 1. It's really a combination of all the possibilities. So that's a very, very rough way to think about what superposition actually means. The other big concept in quantum is this thing called entanglement. And so what entanglement means is that two different qubits, two different atoms, could actually be entangled so that the actions of one has impact on the other one, even if they're separated by very long distances. So this can be quite weird to wrap your head around, but it basically means that you have a system of two things that are very highly coordinated, and that can be very useful because you can look at one thing and be able to determine what the other thing is doing, even if you can't see the second thing. So when we talk about quantum advantage and what quantum is going to bring to technology generally, what we're talking about is how both superposition and entanglement are going to be able to power these quantum computers in a way that's more efficient than what we have in the traditional world. And one thing to keep in mind is that this isn't just a better way to do traditional computation. So when we think about quantum, we often talk about exponential advantage, and this is because we're not trying to just double or even triple the processing power. This is really trying to go from polynomial scale to exponential scales in terms of efficiency. And of course, what that means is the computation that would generally take tens of years, maybe even hundreds of years, would be reduced to weeks, maybe minutes, and really make possible the type of computations that are completely outside the realm of possibility. So that is the goal. That is the big hope for quantum computing. The big question is, when is this going to happen? So it's almost impossible to have any sort of discussion about quantum without having a conversation about timelines and when this will happen. So there are a few things that are driving that timeline. And one thing to note is that quantum computers that exist today are still very, very basic. So most of them are great for exploration. They're great for learning about quantum systems. They are not powerful enough to do any sort of computation that's going to have a commercial advantage or a practical aspect at any sort of scale. So what researchers and engineers like me have been working on are different ways to build qubits, right? The different ways to harness nature, different ways to build qubits from electrical circuits, for example, in the case of superconducting qubits, just different approaches to solve two issues. One of them is how to make these qubits better, how to improve fidelities, which is how accurate it's going to impact how accurate your computation is at the end. And then the other thing that we're trying to solve for is also how to scale from a few qubits to many, many number of qubits. And one thing to keep in mind is that you actually need both. You can't just have thousands of qubits of low quality, and you're not going to go very far with just one very high quality qubit. So it's trying to optimize on those two axes that gets very, very difficult. And that is really the main driver of the timeline for when we will have a large quantum computer. The holy grail in quantum is creating these things called fault-tolerant quantum computers. And that means that even though there's going to be errors in a computation, because quantum computers are very susceptible to the environment, we can actually correct as we go, and the computation at the end is still going to be correct. So this concept of quantum error correction is where a lot of the field is focused on right now, and rightfully so. And it's really the key step to have fault-tolerant quantum computers. And in turn, having a fault-tolerant quantum computer is going to determine when we need to start worrying about some of these big things that quantum computers can do. One of the things that has dominated the conversation in a way is the impact of quantum computers on security. And the reason for that is, you may recall I mentioned that quantum computers can do certain types of computation more efficiently. One of the things that they can run more efficiently are algorithms related to breaking encryption standards. So everything that we currently do, every day you are using the internet, you're doing transactions, all of that rely on your ability to send data in a way that's encrypted, in a way that's secure, send it somewhere else where that is going to be decrypted. So the fact that the standards that we're currently using for encryption would be threatened by quantum computers obviously is something that a lot of people are worried about. But the good news is there are new algorithms being developed. There are new encryption standards being developed. And this is what this category of post-quantum cryptography really encapsulates. And so when we talk about timeline, again, that also is a big driver for conversation, because now you have people on the one hand that are building quantum computers as fast as they can, and then people on the other hand that are trying to adopt these PQC algorithms as quickly as they can before quantum computers get there. So there's a little bit of a race of trying to develop both technologies at the same time. So I'll talk about AI very quickly, just the same way that I baseline on quantum. So unlike quantum, where it's really about doing things exponentially faster because of the different way of processing, with AI, what we're trying to do is mimic the human brain in some way. We're really trying to get away from programming answers and really get to spaces where machines are using that pattern of learning from data and being able to make predictions based on their learned behaviors. So as probably many of you know, there are many different categories within AI. It's a little bit unfortunate in my view that LLMs, large language models, have been really dominating the conversation, as there are different very interesting things that are being done in the AI space that don't really get a lot of voice these days. But at Sandbox and in my work, we're really more focused on things like machine learning rather than LLMs. It's really not about generating data or generating information using LLMs, and much more about using machine learning to make better predictions, to make better diagnostics, and to just help us more generally with cleaning up of data or trying to get insights from data. So what I'm really focused on in my work, and the area that I find really fascinating, is how these two topics come in. And one of the areas that I'm really excited about, we've talked about quantum computing, but there's also this other thing called quantum sensing, which is slightly different. So they both leverage quantum mechanics, they both leverage quantum systems, but the big difference is with quantum computing, you're using these quantum mechanical systems to process information, to do computation. With quantum sensing, you're using the quantum systems to make measurements about the world that's around us. And you can use quantum sensors to measure many different types of properties. You can use them to measure magnetic fields. You can use them to measure electrical fields. They can be used to measure gravity, and a lot of people are working on that. What we have focused on at Sandbox are measurements of magnetic fields because they have a lot of different applications. The image that you see there is actually something called a diamond vacancy center. And what's being shined on it is a green laser, and it's being reflected red. That's why there's the two colors. But these diamonds have very unique properties that make them very good quantum sensors. Incidentally, they can also be used for quantum computing, but we are using them as quantum sensors. So where does the AI come in with a quantum sensor? The quantum sensor is very good at detecting things that is around it, so picking up a lot of signal. But then what you get is a lot of noise also with that. It's very hard to figure out what is the thing you're trying to measure in all of this data that you've gathered. And this is where we found that machine learning and having really good models that have been trained on the surroundings and have been trained on the different spaces and technologies that you're looking at can be very useful because it helps you get from that raw data that's very noisy, it's full of things that you don't care about, to having something that actually gives you an insight about what you're looking at. So to give you something tangible as an example, one of the things that we're looking at is detecting magnetic fields inside the human body. And so some of you may know that we all have magnetic fields inside our human body. They're very weak, but they are detectable. And if you have a magnetometer that is sensitive enough, you can actually pick up what the signal is, and looking at that signal, you can also use that for different diagnostic reasons. What we've been looking at primarily is how that can be used to make measurements with people's hearts. So right now, the main way to diagnose heart attacks or cardiac problems more generally is EKGs. So this is where you get little sensors that are measuring your electrical field, and you get that chart, and it tells you whether things are good or bad. The problem with that is electrical signals, as they travel through the body, actually encounter a lot of resistance from tissues, whereas magnetic fields don't have that problem. So being able to pick up the magnetic field is actually very useful in that it gives you a layer of data that you wouldn't get from EKG alone. So again, taking together the hardware, which is the quantum piece, the quantum sensor, and it's quantum because it's leveraging quantum mechanical properties to measure the magnetic field, but then layering the AI on top of that to take all of that data from the human body and figure out how to process that data so that when a clinician or a doctor looks at that data, they can actually tell, is this normal, is this not normal, and be able to diagnose whether the person is having a heart attack or not, even though the EKG is actually looking normal. So that's the type of powerful application that we're looking at in the healthcare space that brings together these two technologies. Another one that I'll mention very briefly, because we have another talk on that topic, is around simulation. So this is another area where quantum and AI can come together to just give us a really good sense of what's going on. Simulation is very impactful in healthcare because the drug discovery process is a very long one. And what we're trying to do is use simulation to triage through drug candidates faster. So it's a cycle of trying to identify candidates, then they go through different phases of clinical trials to look at efficacy, to look at side effects, and so on. It's a very long process, so what we're trying to do is make sure that that process is shorter, and one of the ways that we do that is by combining quantum-inspired approaches, quantum-inspired algorithms, to simulate molecules better. So doing all of that on the computer before anybody gets in the lab and tries to manufacture these chemicals. So reducing the pool of candidates is one thing. And then also figuring out how those candidates that we come up with interact with different things, how they interact with other molecules, how they interact with protein or targets inside the body, also gives us a sense for what the molecular structure is going to be, what kind of drugs are needed to take advantage of the structures. So that's another way, again, that AI and quantum just really come together for something that's going to be very impactful in the pharmaceutical and healthcare space. So to wrap up, again, one of the key messages that I want to bring up is the fact that we often think about quantum and AI both separately as buzzwords, and in some ways they have become that, but they are also very transformational technologies. And again, the key to making sure that we get to practical applications like the ones that I've mentioned in simulation and sensing today, as opposed to 20 years from now when we do have those fault-tolerant quantum computers, is to think about how the two technologies can be enabling technologies for each other and how we can leverage both in the same system. So thank you, and I look forward to the questions.
Thank you so much, Nadia. We've got some time for Q&A. Excuse me. The thing that I wanted to ask you about is post-quantum encryption. So what does it mean when so much of our data isn't right now being encrypted to protect intellectual property, if you're, for instance, doing drug discovery or national security issues, speaking to your previous work on that. And let us imagine, we don't need to name countries, I'm sure many countries would be involved in this, would be hoovering up as much data as they can, even encrypted, in the hopes of being able to one day break it.
Yep.
What is the plan for a post-quantum world?
Yeah, a great question, and it has many aspects. So you're referring to something that we usually call store now, decrypt later attacks. So this is something that both governments, but also companies that have highly sensitive intellectual property, highly sensitive data, or industries that are regulated. So the financial sector, healthcare sector, for example, they actually have they have numbers, like how many years they have to keep that data secure. So they can't just count on the fact that progress on quantum computing is not going very fast and therefore the data is safe. They do have to protect the data today. So one of there's really two main ways that companies can address this, and they need to do both. One of them is to start migrating to quantum-resistant algorithms or post-quantum cryptography. It's not that hard once you know where your encryption is vulnerable, but that's the hard part. So I worked in cybersecurity for many years, and most chief information officers or most CISOs would tell you that one of the biggest problems that they have is lack of awareness of what's going on in their network. And with encryption, that's a really big problem, especially because as the user of encryption, you don't control who picked that algorithm, right? So it might very well be something that had already been deprecated 20 years ago, let alone something that's vulnerable to quantum computers. So bringing that visibility, giving them the tooling to be able to see all of the different types of encryption that they have on their networks, and then take action to remediate, use one of the PQC algorithms. NIST has done a fantastic job at doing this exercise where everybody, the entire community has contributed in an open source way to these new standards, and now it's a matter of adopting them and starting to deploy them. And then, of course, the second thing is securing the data in the first place, right? To make sure that data at rest is also protected.
So one of the things that I have been hearing, not just here at CogX, but in my other work as a researcher, is this question, the primacy of the integrity of the data set, particularly in artificial intelligence, what you are training your data on. And the National Cybersecurity Center in this country on the 30th of August did 2 new blog posts that you can read online. I invite you to do so if this intrigues you, talking precisely about deliberate poisoning of data sets, very difficult to detect, no fail-safe mitigations, and warning that people should be a bit cautious before rushing in to integrate large language models into their operations. I just throw this provocation out to you from your colleagues here in London. What should people be thinking about in the rush to generative AI, and also just thinking about data in general, which can sometimes feel a bit boring, but is actually the building block of all of this? How do you protect data at rest? How do you protect data that you are using to train your algorithms?
Yeah, that's also a great question. And so there's 2 things. There's security, but there's also compliance. And for both of those things, companies that are adopting these LLMs really need to understand where the data comes from, what the training models have been trained on, and that's usually a blind spot. That's not often something that's revealed. So unfortunately, a lot of companies now have policies where they just can't use these LLMs that were developed outside. I think the open source community has a big role to play here. Just bringing that transparency to the equation, I think, is going to be great. But it's really not going to be a problem that's solved right now. The other thing I would say is, don't rush to an LLM. Like, if you don't need an LLM, as I hinted at, unfortunately, a lot of companies that are interested in AI are just jumping to LLMs right now because that is the buzzword. But there's a lot of other really exciting stuff that's happening in AI, and I hope that they consider that as well, and really focus on what is the problem and work backwards from that, as opposed to starting with LLM and then try to use it.
And what about this whole thing of, like, in cybersecurity, they say you're only as strong as your weakest link? So given that so many people and companies, I don't know about you, but it feels like a day does not go by that some company hasn't had their data accidentally leaked by someone, or someone clicks on a link, or it's a ransomware situation. Some of these very serious hospitals, Hackney Council here in London, many places in the United States have just not been able to operate and have had to go back to paper. So given the state of play, clearly we're not telling the cybersecurity story well enough and empowering the population to keep themselves safe. Going into a quantum discussion is almost like running before we can walk. So what would you say if you could design a world in which we're going to be really cyber secure and everybody's savvy? What are the things you wish people knew and how they could empower themselves?
Well, I mean, first, I hope that they don't get so overwhelmed that they go back to paper, because that is not the right solution. But I think considering your key assets. So when we work with customers, that's one of the first things that we try to figure out is, what are you really trying to protect? Is it the network itself? Is it the data? It doesn't have to be a one-size-fits-all. So usually the organizations that are best at consuming cybersecurity are the ones that are the most knowledgeable about their network, about where the vulnerable things sit on the network, and they're able to segment and use different approaches for everything. Because there's always a trade-off. So even with some of these, new cryptography, these new encryption protocols, for example, one of the things you might be trading off is speed. If you increase the size of keys or you make the key generation more complex, you're going to be trading off performance. That might be perfectly acceptable for some of your applications, but that's not going to be acceptable for IoT devices, for example, or something where speed is really a requirement. So again, starting from the use case and be flexible on the tooling is really the key.
And final question, I know we've only got 36 seconds, so I'm going to be fast and efficient, I hope. There's a worldwide shortage of cybersecurity talent.
Yes.
What do we need to do to get more people into this field and understand the role that they can play in keeping us safe? Because we're only going to be having more data and more AI, et cetera, and the idea that it's going to be more and more, but also less and less secure is not great.
Well, and actually, I think the answer is a little bit in your question. So we have a shortage of cybersecurity expert, but we also have a shortage of AI expert, and we have a shortage of quantum experts. So what I would love to see is actually more discussions on how all these disciplines actually cross together. And the more we can educate people on all three, they don't have to be experts in all three, but if they're knowledgeable and they can differentiate between quantum hype and quantum reality, if they're able to say what the right type of AI tooling is right for the type of application, it's going to make them that much stronger of a security expert. So I think part of it is in the recruiting side, also letting people be able to diversify the skill set and they don't have to come to security through the traditional IT professional route, right? They can come to it from more of a deep tech, from more of a technology focused angle as well. We have those people on our team and they've been wonderful because they're usually they've been trained as quantum or they've been trained as AI expert, and now they're seeing how that impacts security more generally, and it just makes them very great customers of the technologies and great developers of the technology because they have that multidisciplinary perspective. So I think that's part of the answer.
I could talk with you all day. I'm so sad that you have to get off the stage for the next person, but I'm going to catch you afterwards. Thank you so much. Please join me in thanking Nadia.
Thank you.